So the problem statement is as follows. When we connect two loads, one can be in one line with a string over a horizontal rod, and when we release the light load, it will sweep around the rod, keeping the heavy load from falling to the ground. So we are to investigate this phenomenon and discuss the relevant parameters that govern the motion of this system. So this is the brief flowchart for our presentation. First, for the observation, I will start my experimental setup and then discuss about our key observations about the phenomenon. Second, I will move on to analyze the motion. We will divide the motion into two stages and give a qualitative explanation on the stage transfer between these two stages. And then finally, now we derive the equations of motion governing these two stages. For the experiments, we will be matching our theoretical simulation to our experimental data, and more information will be given in these further experimental sections. Now, for the conclusion, we will discuss the critical condition for looping that we will define, and then summarize my solution. So this is our experimental setup. We use a horizontal rod that was previously leveled, and we hang the string over the horizontal rod. And if you see here, there's a stand behind the light load that will provide a precise initial release mechanism. And more explanations will be given if further questions are asked during the discussion section. And for the video analysis method, we use the computational pixel counting method as a tracker. And so here are our key observations. We were able to see that under certain initial conditions, the heavy load stops at a certain point, the light load will loop around the rod. And based on these observations, we now divide the stages of the motion into two stages. First, the slip phase, the light load will be pulled. The string attached to the light load will be pulled by the heavy load while the light load is sweeping, and the heavy load will descend. And during the non-slip stage, the heavy load will stay stationary while the light load will loop around the rod on its own. And the conversion between the slip state and the non-slip state can be explained by the following two qualitative explanations. First, due to gravity, the heavy load will descend while the light load will sweep due to the gravitational restoring torque. And first, the decrease in the sweeping radius with gravitational restoring torque will induce faster sweeping of the light load due to the angular momentum conservation principle. And due to this faster sweeping, the tension attached to the light load will increase, thus causing the heavy load to stop. And for the second explanation, as the light load will sweep, the wound angle of the string onto the rod will increase. And this increased wound angle will cause an additional rope friction that will eventually cause the T2, the tension of the string attached to the heavy load, to increase, thus causing the heavy load to stop. So now we derive the equations of motion. So first, for the light load, we use the Newton's second law in the accelerating frame of the string rod contact point over here. So, writing the force equations in the radial and tangential directions each, we can get these following equations. Where the small r denotes the sweeping radius of the string connected to the string from the point of contact of the string and the rod and the light load. And in this equation, I load denotes the moment of inertia of the physical mass of the light load. And for the heavy load, we write down the force balance equation in the vertical direction, where T2 denotes the tension of the string attached to the heavy load, and the L denotes the length of the string attached to the heavy load from the string rod contact point. And also, we can impose an inextensible string constraint that says that the string will be inextensible. And for the rope friction, the tension around the cylindrical rod at rest can be described by this following equation that describes an exponential increase of the tension related to the wound angle. And this equation is applicable for only stationary cases. However, in dynamic cases, such as the slipping state that I have talked about earlier, the string and the relative motion between the string and the rod is non-zero. Therefore, we cannot apply this tension around the cylindrical rod at the rest case. So we modify this. Rope friction equation. We modify this rope friction equation for the case in motion, which can be written as the following equation. And under the approximation that the linear density of the string is negligible compared to the tension term, we can approximate this to a similar form of the equation that we have discussed earlier. So by defining the mass ratio between the light load and the heavy load as kappa, we can write down the equations of motion describing the motion of the heavy load and the light load each. And also the coefficient of kinetic friction in here was determined in an experimental way, and more explanations will be given if further questions are asked during the discussion section. So now we move on to our experiments. First, the experiments can be divided into three main parts. First, we compare the trajectory between our theoretical simulation and our experimental data. And in the second section, we will compare the sweeping radius versus height mass by varying these initial parameters and observing the effect of each parameters on the effect of the motion. Third, we will draw an energy transfer diagram which will clearly show an energy transfer between the heavy load and the light load H with respect to time. So for trajectory comparison, we can plot our theoretical simulation that has been performed using Python based on our equations of motion that we have derived earlier. And plotting the experimental data points above these theoretical curves, we can see a good agreement between our theory and our experiments. And playing the video that we have overlapping the experimental video and the theoretical simulation, you can see a very close agreement between theory and our experiments. And plotting the radius against time, you can see a clear stage transfer between the slipping phase where the R will decrease steeply and the non-slip phase where the R will decrease gradually compared to the slipping phase. And this has been also verified experimentally. And also comparing the radius time graph with varying the two different mass ratio, kappa 1 and kappa 2, we can see that when the mass ratio is greater, the rate of decrease of the radius will be smaller because due to the greater acceleration due to the smaller acceleration by the mass of the heavy load. This has been also verified experimentally. And so we have performed experiments varying the initial strain length L0 and the initial release angle theta 0. And comparing these initial angles, we were able to divide the regions into where the looping happens or not. And we divide the looping as when the wound angle is greater or equal to 2 pi. And this black curve was numerically obtained by our simulations. And these each dots correspond to our initial experimental conditions, where the green dots denotes that the looping happened, and while the red dots indicate that the looping did not happen. So our experimental data show that this boundary. So our experimental data shows that our numerically simulated boundary will fit with our experiments. So if the initial string length will be too small, there will be not enough energy transfer from the heavy load onto the light load for the light load to complete the loop around the rod. And if the initial release angle is too small, there will be not enough gravitational force exerted onto the light load to acquire enough angular momentum to loop around the rod. And also testing three different rod radius. You can see that the rod radius does not heavily affect the slip phase as shown in this part. However, the non-slip phase is being affected heavily by the rod radius. As you can see, that the time duration for the non-slip phase differs when we differ the radius of the rod. And this can be explained by the following analogy. If the rod radius is greater, while the light load sweeps around the rod, the rate of the radius decrease will be proportional to the rod radius. Thus, if the rod radius is greater, there will be greater wound length in time. Thus, the rate of the radius decrease will be greater. And by testing the two different coefficients of kinetic friction, we can see that if the kinetic friction is greater, the light load will stop slipping faster, and there will be a more longer period for the non-slip phase. And this can be explained simply by when the coefficient of kinetic friction is greater, there will be smaller acceleration, so that the magnitude of the rate of decrease of the radius will be smaller. So finally, we can plot the energy of the light load and the heavy load each, and the total energy against time. And if you see here that we can see a clear phase distinguishment between the slipping phase and the non-slip phase. And we can see a clear energy transfer between the heavy load and the light load during the slip phase, and no energy transfer in the non-slip phase. Also, there will be total energy loss due to friction between the rod and the string. Now, for conclusion. So we will discuss the critical condition for looping. First, the theta 0 has to be higher according to our numerically simulated curve by varying the initial string length, the initial angular force. And based on the same graph, we will be able to deduce that the initial length has to be longer. And for the mass ratio, based on our experiment and simulation, we were able to deduce that the mass ratio has to be high, but not too high, because the light load has to stop before the light load collides with the rod. And also for the coefficient of kinetic friction, there can be a similar analogy. The coefficient of kinetic friction has to be smaller because more energy from the heavy load has to be transferred onto the light load or the light load to completely loop around the rod. However, the photoreceptor connection needs to be not too small because the light load has to stop before colliding with the rod. And for the radius of the rod, we were able to observe that the radius of the rod does not have a clear effect during the slip phase. Rather, the radius of the rod affects the rate of the radius decrease during the non-slip phase heavily. So to summarize my solution, I divided the motion into two phases: the slip stage and the non-slip stage, where the relative motion between the string and the rod is present. The non-slip motion, where the heavy load is stationary and the light load will loop around the rod on its own. And second, we direct the coincidence motion and perform simulations based on these coincidence motion using Python. And by accurately measuring friction coefficients, we were able to see that our theory and experiments are well matched. And also, we vary parameters along with qualitative explanations on the role of each parameter. And finally, we determine the critical condition for looping. These are my references, and thank you.
Okay, use slide number 3.
Slide number 3?
Yeah. So, on the video we saw, please open the video. So, we can see that during the motion, your light load hit the string of the heavy one. So, did you include those experiments in your data?
Oh, I did not.
Okay, thank you. Did you launch your light load perpendicular to the rod? So, what the oscillation plane perpendicular to the rod?
Oh, the motion is happening, the plane that is perpendicular to the rod. That's correct.
Okay, thank you. And did you include that your string could wrap around itself and change it?
The string will be able to wrap around itself, but I think the effect was very minimal because the string thickness is very thin.
So you didn't include it?
I did not include it in my theoretical model.
Okay, thank you. Please slide number 26. So here we see the comparison between experimental and theoretical energies. So how did you calculate your energies experimentally?
Oh, energy. The energy can be divided into obviously the potential energy and the kinetic energy. The potential energy was calculated according to the y coordinate of the system. The kinetic energy was calculated by the velocity.
Okay, I got it. Thank you. Please slide number 23. So here you showed us the observability regions. So what condition did you apply to those curves to get this together?
You mean the what initial conditions?
Yeah, not the initial conditions, but what do you mean as looping to get those curves?
Can you repeat your question?
What conditions are applied to get this curve?
Conditions. So the mass ratio was.
Thank you.
I believe
Time's
wrong.
over.
Yeah. to my opposition to the problem, Bloomberg pendulum. So for the first, let's do the full summary of the report. So, well, the theoretical model, I think it was quite right. So, the reporter used the sigma function to define the dependence between the thread tension forces. But actually, I quite disagree that inside the function of sigma, you look for a difference between those tension forces, but not on the velocity, which is quite crucial because when you have a friction force, it is directed counterwise then to the velocity. So also he used an inverse equation, and the main advantage of the theoretical model was that he calculated the observability region, but during my qualifying questions, he couldn't explain that condition that was applied to that curve. Also, he investigated really large amounts of parameters such as mass ratio, the length of the thread, and so on. But the experiments, I suppose, wasn't quite good because, as you saw on the video at the very beginning of the presentation, we saw that the light load connected with a string. And also, the most major disadvantage of the experimental part was the fact that the string wrapped around itself. It changed the friction coefficient, and that's why we can get the same data after repeating some experiments again and again. So also the theoretical part, I think the main disadvantage of it was that there was missing the phase-space diagram, which could predict all the motions of their pendulum, but if they got a full mathematical model which compares with the experiment really well, when we can show it to us? That's what I really missed in the theoretical model. And also about equality, I think that defining only two stages of motion isn't enough. So we'll discuss it later. And also, there were no explanations why the light load sweeps around the rod. And the task of the problem asked us to investigate the motion of those loads and explain this. So there wasn't explaining why the light load could such easily stop the heavy one when the mass ratio is really high. And also the sweep. Why when the light load continues to move, it sweeps around the rod, and also it wasn't explained, unfortunately. And also the boundary region wasn't explained. Like, of course, the reporter showed us the observability region, but he didn't explain us why that this region appears. What factors cause those observability region? And now I want to move to the discussion, please. So, my first question will be about the moment conservation law. So, during your lot of explanation, you said that your pendulum, your system, could be described with a momentum conservation law. So, why do you think that's it would be applicable here?
Very short.
Oh, yeah, sure.
Because there are an external gravity force acting on the light node, the angular momentum will not be exactly conserved. However,
Well, but you said that's
it was an angular momentum conservation principle, not the actual quantitative law.
So please explain this.
Okay. So as the light node sweeps around the rod, there will be a gravitational restoring torque acting on the light node. So that because there is an external torque acting on the light node, the exact amount of the angular momentum will not be exactly conserved. However, when the string slips, the radius, the sweeping radius of the light node will decrease. So due to the decreased radius, due to the angular momentum conservation principle, the light node will sweep faster.
Okay, thank you. I got it. So personally, I quite disagree with the reporter. So he explained this fact because of some law like momentum conservation law. But as he explained, I could say that it just happens because of the formula which could be given, like the tangential velocity will be equal to the angular one multiplied by the distance from an axle to the load. So of course there will be not momentum conservation law. That's not.
So do you think the angular momentum of the light load is not conserved?
Yes, should, because there is a gravity force,
Oh,
and
okay.
while your light load sweeps around the rod, some amount of string which is wrapped around the rod loses, so the momentum doesn't conserve. Isn't conserved. So now I want to describe the motion phases. So your theoretical model, as far as I can tell, predicts only two stages of motion: when the heavy load stays in its equilibrium, and when the light load when the heavy load falls down by it and drag the light load up. So how do you think? Are these all of the possible motions?
It is not, and not on the two phases, there also exists a reverse slipping phase, where the tension attached to the light load is strong enough to lift up the heavy load, and the
Yes, true.
then the heavy load will slip to the opposite direction. And we have also qualitative to explain this, but when the tension is too weak to hold the heavy load, or too strong enough to lift up the heavy load will stop. The heavy load will start to move after the non-slip state has begun. And we have our experimental data that show that this third phase is also visible. In an energy transfer diagram,
Okay.
the three states are obviously visible. However,
Wait. That's not exactly what I'm asking. I'm looking for when your system evolves,
yes.
Your light load could start to sweep such fast to drag the heavy load up.
Yes. So this is about the dragging the heavy load up, so that the total energy of the heavy load has increased due to the drag being dragged above.
Okay, thank you. And does your theory? Oh, well, okay. So I should say that that's quite good that the reporter investigated those motions, but it wasn't presented during the report. He just said that he has two phases of motion, but he didn't explain how his function signal interacts with those different types of motions, like when it will be equal to 1, -1, or 0, and how the value of signal will influence on the phase of motion. So now I want to discuss qualitative part of the problem. So please again open your slide number 23. Yes. So could you tell what do you mean as looping, and how do you define those observability curves?
So I define looping as when the Wald angle is not greater or equal to 2 pi, so that the light load has completed one loop around the law.
Okay, but don't you think that it will be better to investigate what was asked in the problem statement? So the problem statement tells that the light load could start the heavy one. So could your theory predict the motion, the observability region for the phenomenon which was given in a problem statement? Why, when the light loads will start the heavy one falling down for a long period of time?
Okay, so for all our experimental conditions that correspond to these points, so when the Wald angle was over the 2 pi, there was enough row friction between the string and the rod to stop the heavy load, or the light load to stop the heavy load. So this definition will correspond to the stop of the heavy load too.
But wait, do you assume that if the wrapping angle will be 2 pi or more, the heavy load will be always stopped?
No, for our experimental conditions, for our experimental coefficient of kinetic friction, that when the Wald angle was over than 2 pi, then it was great. The factor was greater than the gravity factor in the mass of the heavy load, so that this Wald angle was enough for the heavy load to stop. But I expect when the coefficient of kinetic friction is too small, the light load will not stop.
Could your theoretical model predict the motion and the observability region when, for the motion phase, when at the end of the whole motion, the heavy load stays in the equilibrium, and the light load starts sweeping.
So you're asking that when the light load does not collide with the rod.
Well, it could collide at all. So because your observation curve,
Yes.
you're saying that if the reference angle is higher than 2 pi, then any weight will observe the stopping of the heavy load.
Yes. Yes. For our experimental conditions. Yes. But what I expect when the coefficient of kinetic friction is too small, then our experimental condition is that the definition of this looping has to be modified.
Okay, and will this looping angle always stay the same? For example, if we'll change the friction coefficient or mass ratio, will this?
It will change, but for our experimental condition, this was an adequate definition for the looping.
Well, okay, but for example, if you'll change the initial angle, as is yes, as it is shown here. So, for example, if we'll launch our light load from some angle, and during his motion, of course, he did correct around 2 pi, and then it's the heavy loads will not stop because the energy of those because of the energy transformation, the heavy load wasn't stopped.
Could you explain more?
Wait. Okay. So you're saying that for your experimental conditions, the reference angle it will be equal to 2 pi.
If the wrap angle is above 2 pi, then the
Okay.
angle will stay.
How do you define those reference angle? Why it is equal exactly to pi in your case?
It was just my definition because the 2 pi is included to complete the one loop
So,
under wash. And in this condition, the heavy load has completely stopped, and this condition is satisfied.
Well, anyway, could you explain why do you have exactly 2 pi for your system?
It is not exactly 2 pi, but this was an adequate
Well,
condition for determining the looping.
Well, you said that this curve is defined by reference angle 2 pi.
Oh no, so this okay. So there was some misunderstanding. So this direct curve is obtained when the phenomenon has when the system has stopped, meaning that when the light load has collided with the rod, or the heavy load has descended fully, then we could get the value of the final longest angle. And the final longest angle is over than 2 pi.
So,
I define as looping.
personally, I think that to get the observability region exactly that was asked in the problem statement, to get this curve, you should apply a condition that when the light load touches the rod, the velocity of the heavy one should be equal to 0, but not the but this phenomenon shouldn't be based on a reference angle. And so my last topic will be about the perpendicular launch. So you said that you launched your light load, the plane of oscillation was absolutely perpendicular to the rod. So don't you think, and we've seen it in your experiment, that during the motion your light load could hit the string of the heavy one, or they collide?
Okay, it is possible, but when the light load collides with the string, or it collides with the heavy load, then the phenomenon presented in the problem statement will not be presented at all. So I have not analyzed these cases.
Okay, thank you. Personally, I think that there should be some initial angle between those plane of oscillations and the rod.
Thank you. Now summary.
Okay, thank you. So I want to summarize my discussion. So doing this, we've described the motion and the condition for sweeping. We also defined the condition that should be applied to get the observability region. We've described that the perpendicular launch can be used in this situation. And also we talked about the momentum conservation law, and I think that anyway it couldn't be there because there is a great gravity force, so the system is not conservative. And during the run around the rod, the amount of swing decreases, and that's also
Thank
because
you.
the momentum is very strong. Thank you.
So, first of all, question to the reporter. What's the condition in which you can say that angular momentum is conserved?
The angular momentum is conserved because there is no external force acting onto the system.
And now question to the opponent. If you talk about our system and see about the torques from the center of the rod, what are the forces that has non zero torque?
Wait,
So you say that angular momentum of the system is not conserved. What are the forces that have non zero torque?
Well, if we look,
Just a few words.
that's the gravity force.
And I got it. So now question to the reporter. What was the method of friction coefficient measurements?
the value of the coefficient of friction measurement. So, do you just want the value or how the coefficient of friction was measured? The coefficient of kinetic friction was about 0.185 for positive y.
I got it. Now please frame number 20.
20?
20, yeah, 2 zeros. As you can see, wait. Now it isn't so good agreement between theory and experiment in dynamics.
So the discrepancy with the end of the phenomenon we were asking about.
Opponent, how do you think? Please the video, please again. And while it question to point, why do you think what's assumption? No, video. Not yes. What is the reason for bad dynamic physics now? See.
I think that's
And
because maybe that's because of air drag.
Okay, think I got it. So what was the distance with the rod in your experiments?
The radius of the line.
To the camera, what was the distance from the camera to the rod?
Oh, it was about 1 meter, but I have accounted into parallax errors from the video analysis.
And opponent, do you think that 1 meter is enough to not take into account parallax effect?
I think not, because the perspective could change the results significantly.
Thank you very much. You say that what you said on certain frames that your string is inextensible. Did you check it experimentally somehow?
Yes, I did.
Any proof?
And the maximum tension gradient in the system was about 1 Newton. But if the 1 Newton was applied to the system, I found that the stretching of the string was very negligible compared to the length dimensions of the system.
And now question first of all to opponent. What is the center of rotation for light load in the system?
The collision points between
No, center of rotation in which point of time? So on this picture.
for example, here for the light load, that's the collision point between the rods.
And for what do you agree with it? Yes or no?
Yes, I do.
I got it. So,
Thank you. Time's over.
about to investigate why type nodes route around the road. According to the report, I totally disagree with his qualitative explanation based on angle momentum conservation. Because of gravity force, and if you talk about the focus question about the center of the rod, it's also not zero question of tension force. So it's impossible to say about the angle momentum conservation. It is not so strong point of the report. What was the main results that the report gave in his work? First of all, it was the question of motion of the system. It was a very good theoretical model with the difference between static friction and kinetic friction. I agree with this part. So to perhaps the question for this compared theory with experiment, it was really good agreement with, for example, how the distance. So even good agreement how the energy of the loss changes to 7. But on the metrics frame, see that it isn't so perfect agreement between theory and experiment. I think it can be first of all because of not so good for neglecting a friction, extensibility and the string, and the subjective component of the motion. After the model that predicted all these differences, and some compounds of critical cases, for example, depends between length and the angle. But it didn't investigate how the mass relationship affects the phenomenon, because it's of course not with all mass relationship phenomenon in that zone. So talking about the process of the report, the main process there was boundary condition for relationship between length of the light flow stream and the angle, but not the mass ratio. That we found out the two motion, the two stations of motion, and describe the energy transfer. But for concepts when it is angular conservation, that's totally impossible to use in this problem. Not to mention why have a low stop on qualitative level. Dynamics was investigated only in two dimensions, and we don't believe that in his experiment through the part of the corner was over controlled. So it was also with respect to the effects somehow, because one link is too small in this problem. Connection of float was done. We don't agree with the qualitative explanation because the algorithm isn't conserved. And not all of the problem was investigated because there are much more modes that he investigated. He investigated only one mode, but there are about 4 in this problem of even 5. So to talk about the opponent, his position, he talked that qualitative explanation is not so good. I agree with it. Talk about the existence of much more boundary conditions. I agree with it. Notice that law of conservation in the momentum isn't good there. I agree. And the theory was correct. But for not so strong points, we didn't saw that there isn't such good agreement between dynamics of the system, so how the coordinates of the loss change the time. And his question was also very good. For example, he's seen on such frame how light force strikes the rod that gives us lots of question about experimental methods and why it wasn't taken into account the theory was presented to us. So what was the discussion? They talk about violence phenomenon is observed, so about the positive information. We posted that angular momentum, opponents said that it's because of the tangential velocity becomes constant. I don't agree with both of this ways because tangential velocity is also changed with the gravity amount force. Angular momentum is changed by force by 2 to 4. They describe different modes, but not all modes are in this phenomenon. And finally, they talk about the conditions on the curve of boundary conditions. It was not so good, I think, not so relevant topic in my opinion. And finally, about the conflict question was the center of rotation. Both of them show that they don't really understand the problem because if they say that this point is center of rotation, it means that light flow don't have velocity in this direction.
Okay, so for concluding remarks, first I would like to talk about the angular momentum principles that I have brought up in my qualitative explanation. So if you look at here, I mentioned the angular momentum conservation principle to give an intuitive explanation about the faster winding of the light load. And because the origin of the system is at the center of the rod, the center of rotation of the light load is the consequence between the strain and the rod, the angular momentum itself cannot be well defined. However, to give an intuitive understanding of the phenomenon, I have borrowed the concept of angular momentum conservation principle. And the actual quantity of the angular momentum will not be conserved due to the external gravity force acting onto the system. And for the z-axis motion, if the z-axis motion is present, we can expect that the winding the winding cross section of the string with the rod will be elliptic. However, when we have given an initial displacement angle of the z-axis, we were able to observe that the eccentricity of the we were able to compare the ratio between the circumference of the circle and the ellipse here, and we were able to observe that the ratio was very equal to 1. So we have approximated this to a circle. Thus that our experimental conditions were suitable for our theoretical model. And so the reviewer pointed out that I have not described the stopping of motion of the heavy load. However, in my qualitative explanation, the increased tension of the T1 and the greater rope friction will eventually cause the tension of the string attached to the heavy load to increase, which will finally stop the heavy load. So I have completely explained the sweeping motion of the light load, the stopping motion of the heavy load too. For the air drag that the reviewer mentioned, because the time scale of this phenomenon is very small,
Okay, thank you.
we were able to see that there was collision.
All right, now the question comes from Gerard. Anyone would like to ask any question?
Yes.
Yes, please.
As the capstone equation from the first for the rope friction, he investigated the research. What is your suggestion for the computation of the friction as the smaller?
So the direction of friction will depend on the velocity at any given moment of time. So the Eller's
Can you make a short answer, please?
the Eller's formula say that this connection will be proportional to the initial thread tension force to the exponential if the heavy load falls down or if it moves up. But if we want to revert the situation and find the minimal force to keep the heavy load in its equilibrium, we should use the inverse exponential function. So, so the formula with the
Oh, okay. I think she gets your answer. I have a question for the reporter. Can you show me how you measure the kinetic friction coefficient?
Kinetic friction.
Yes.
So I have constructed a rope flow system that following diagram shows, and we have used the rotary motion sensor to measure the acceleration of the string between the string and the rod. By using Newton's second law, we were able to get the value of the tension, the two tensions on each side of the string, by measuring the linear acceleration of the string.
Does your kinetic friction depend, the coefficient, does it depend on velocity?
Oh, it does not depend on the velocity.
Okay, and how do you incorporate this finding into your theory? Both kinetic and static frictions.
For the kinetic case,
So you should separate the,
yes.
you don't
So,
have any transition like
no. Strictly, the capsule equation can only apply in the rest of the case
My
because
question is that, like, for the whole phenomenon from stage 1 to stage 2, how the value of mu changes from US from UK to US in your model.
so if the relative motion between the string and the rod is 0, then this equal sign will change to an inequality that states that the T1 cannot exert T1 cannot hold a force that is stronger than this value. So, however, in the kinetic case, we were able to describe the ratio between the tension acting on each side of the string by just following a simplified form with the approximation that the linearness of the strings in which.
So it's more like a state function changing from mu K to mu S.
The coefficient of friction will change like a step function.
Any other question?
So when you measured the extension of the string, then you gave a value for tension. How did you find that value?
I believe that the tension was plotted in the axis. Oh, you mean how I measured it experimentally?
Yeah. The tension in the string during
Oh, it was measured by using a Pascal force test.
yeah, but for the system, because you gave a value for tension.
For a system, well, I estimated that value by our theory by using the value for the velocity and the acceleration of the light mass or the heavy mass.
And the reporter to to start the rotation, what is the initial angle in
Initial
your
angle?
experiment?
The initial angle was ranged from, I believe from about 0.19 radian to pi over 2.
So if you go to your equations of motion,
Equations of motion.
okay, when you use this to compare your theory to your experiments, which parameters did you measure? Which parameters did you fit?
I measured the x and y coordinate of the light lobe and the y coordinate of the heavy lobe.
Okay. Did you have any fitting parameters when you compared?
I did not have any fitting parameters. It was just experimental data.
My very last question on page 20, when you have simulation versus your experiment, is that simulation from that actual video that you showed us?
From
The
the initial
data.
statements, the video was filmed.
Yeah.
Yeah, it was.
Okay. Because I noticed the collision between the string and the rod and the small mass at the very beginning.
Yeah, I believe that the collision between the load and the string may have caused the actual
Alright.
video to lag.
Thank you. Okay, it's not for